Welcome everyone, welcome to IMSE881 Linear Programming Lecture 6 Part 3. And last time we finished Part 1 and Part 2. Today we start focusing on the interpretation of the due variable, what it means to the actually decision making. Look at here, we have a maximization problem. Maximize z equals to sigma of Cj times Xj, okay, Cj times Xj. And constraint will be sigma of sum of Aij times Xj greater than equals to Bei, and B is the right hand side, okay? X are non-negative for all of them. Let's look at the interpretation for the due variable. The corresponding due variable should be on here. So this is the omega. See if I can change that to, okay. So this is the omega. What I have is the due variable. F at the optimal basic feasible solution, xb and 0, xb is the basic variable, and 0 is the non-basic. For the primal problem, the optimal objective function value should be equals to the z star. Z star is the optimal objective function value, and equals to the cb transpose times xb, okay, because xn's are 0. And xb also equals to b inverse times b, so we have this equation over here. But the first part, CB transpose times B inverse, actually equals to omega. So equals to omega transpose times B, or B transpose times omega. Okay? And therefore equals to summation of BI times omega I. If I, using this equation, take a partial derivative respective to the BI, and then BI is omega I in this case. So we can see that any increase or decrease on BI, which is one of those right hand side on this constraint, which is the resources on this constraint, then we will change the objective function by omega I. That's the case. All right. Also, we know if xb currently is the optimal basic feasible solution with no negative rows, 0, okay, non-negative row 0. This is for maximization problem, so therefore it's a non-negative row of 0 entry. And z star equals to the current objective function equals to cb transpose times xb. So we're going to go to the, see, this is the drawing I have. Actually, current z is right here. Currently, when b is right here. And then if I increasing b, I can keep increasing my objective function, but maybe several breakpoints, and then it's not going to change my objective function anymore. That means I have a sufficient BI on the right hand side, which is sufficient resources are, and we don't use up those resources anymore. So it's not giving even more BI will not actually impact my objective function value. Okay, we'll see in that next slide. Next slide, if we the definition we have for the basic variable xb by the following. Okay. By the definition of the xb, current basic variable, what if we can increase one of the resource bi by unit of 1? See what happens. So that would actually illustrate that. All right. So for now, b times xb equals to right hand side b. What if one of the bi I increase them by 1 unit? And that means if I multiply both sides by b inverse, the current solution, basic solution, will be equals to the b inverse times B plus B inverse times EI. EI is the unit vector with the ith row with 1, the rest of the row is 0. Okay, this is unit vector. So the problem is we want to maintain XB is non-negative, then XB is still an optimal basic feasible solution, but recalculate based on the B inverse times EI right here. Let's observe the differences in these two objective functions. We know the Z star is the current optimal objective function value, and the Z hat will be adding 1 unit to the BI vector, okay, B vector. So on the ith elements of a B vector, adding 1 more unit. So the difference between the Z hat and the Z star right here is actually equals to omega. Remember, omega equals to CB transpose times B inverse. We're going to prove you how that's happening. Look at the Z hat minus Z star equals to CB transpose times XB. XB equals to B inverse times B plus 1 unit of BI is going to be increased by 1. So it's equals to B inverse times EI. We have right here. Okay? That's the current solution. And also minus CB transpose times B inverse times B. This is the original optimal objective function value. This is the new objective function value. And the differences will be CB transpose times B inverse times EI. And CB transpose itself equals to omega, and then equals to omega times EI, which is equals to omega I right here. If XB has to be non-negative, we know that currently it is a optimal basic feasible solution, since we have no non-negative row 0 entry, which is currently optimal, and therefore let's look at this result. Since XB has to be non-negative, that means B inverse times B plus B inverse times EI has to be non-negative, and therefore the XB plus the column I of a B inverse matrix has to be non-negative. So that means it depends on the column I of the B inverse, and to determine if the objective function current basic solution need to be swapped out or not. Okay, if it is negative, we need to do 1 more pivot in order to get the next variable in. So what happened if it's let's look at this all together. Review this 1 more time. The problem is maximization problem. Okay, maximization problem with Z is my objective function value equal to summation of Cj times Xj. Our constraint is the summation of Aij times Xj greater than or equals to Bi. Okay, we have total M of those constraints. And also for all the Xj is non-negative, we have total N variables. Aij represent the amount of resources or input needed for produce 1 unit of output. And then our decision variable, Xj, right here and here, are the number of units to we plan on producing or produce. And summation of Aij times Xj equals the amount of resources we're going to be used. Okay, going to be used. And Bi will represent the amount of a resource available for resource I. Cj represents the unit profit for output of I product. Suppose we solve this problem using the simplex method and find the optimal basic feasible solution, XB and 0, and then omega equal to CB transpose times B inverse. then the optimal objective function value should be either equals to CB transpose times XB and also equals to B transpose times omega. And that means the XB and the omega are currently the optimal solution. And also, previous slide we showed that each time we increase 1 unit of a BI, and that's amount of a Z, that's amount of Z we can improve, okay? 1 unit of BI and omega of amount of the objective function we can improve. Some of the question and answer, let's go over, see if we understand the real meaning of due variable. First, supposedly we have omega 3 equals to $500 in our solution. What is the most you were willing to pay for getting one more resources of resources 3? Okay, so for example, now solving this linear equation, programming problem, you get your due solution number 3, omega 3 equals to 500, and that means, okay, your resource number 3 is used up first, okay, and then this is the what? The maximum amount of money you were willing to pay to get 1 additional units of resource 3. So $500 for resource this reason. Omega I is also called the shadow price. Shadow price is providing information about actual price for the resource I. Okay, that's very important information for the due solution. Suppose we use less resource I than it is currently available. If we are able to see more resource I are available, would you expect total profit to be increased? Since we are using less than it is available right now, of course, based on the complementary slackness condition, okay, based on the complementary slackness condition, if this part of the resource is not used up, so this part will be positive value. In order for this equation to be equal to 0, so omega has to be equals to 0 in this case. Remember, the due variable times the primal constraint equals to 0. If it's not used up, meaning this constraint is not tied, we have more resources available, so I'm not going to willing to pay any more money for this resource 3. So that's the conclusion. Supposedly we can increase Z by making resource I more available. Would you expect all the resource I are currently used up already? Of course. If I can increase my objective function value by making more resource I available, meaning currently it is used up. So that means if omega I is greater than 0, based on the complementary slackness condition, it means that omega I is greater than 0, then the equality condition holds for the primal constraint I. So that means the resource I, number I, is used up currently. All right, that's changing the subject. We're going to start talking about due simplex method. The previous discussion what we have, if we change the right-hand side, making a resource more available, but sometimes I will get a negative, the current optimal objective, optimal solution is not basic anymore, it's not feasible anymore. And how are we going to do that? So it's primal infeasible. In this case, we're using a technique called due simplex method. Here we're trying to explain the simplex method for minimization problem. Find a basic solution for now, not necessary to be feasible. Okay, that means right hand side you have a negative value. But all the zj minus cj is less than or equal to 0, and therefore this means the current solution is at the optimal tableau, but the right hand side is has some negative entry. If the right hand side is all non-negative, that I know was all the row 0, zj minus cj is less than 0 or less than or equal to 0, and the right hand side is feasible, which is greater than or equal to 0. Then we stop. We know we're already at the optimal. If not, select a pivot row R with the most negative entry, which is the minimums of xbi, which is whatever is less than 0. Choose the smallest one, most negative one. And also, using the similar pivot rule, but this time is respect to the column or not the row. I'm using the zj minus cj as a denominator divided by y entries, who is negative, not positive in the primal impact. If all the yij are rj are greater than or equal to 0, then we stop. The due is unbounded, and the primal is infeasible. There's no point, feasible solution for the primal problem in this case. And then we're going to pivot on this negative pivot entry, YRK, and then go to step 2 again. So we're looping this. Okay. We're going to give you a numerical example to show you how this algorithm is run. This is my primal problem. Minimize 2x1 plus 3x2 plus 4x3 and subject to x1 plus 2x3 plus x3 minus x4 greater than equals to 3. So that means actually without this surplus variable, this is a greater than equals to constraint. And also 2x1 minus x2 plus 3x3 minus x5 equals to 4. That means also this constraint is a greater than equals to constraint. So that's why we adding a surplus variable here. All the x's are non-negative in that regard. Okay, its corresponding due problem, we can write it out like that. Just simply turn this thing 90 degrees, okay, and the right hand side becomes the objective function 3 and 4, and the objective function originally becomes the right hand side. So I have originally 3 variables, x1, 2, 3, so I have a 3 due constraint, correct? I originally have a 2 primal constraint, so I only have a 2 due variable. Remember, primal constraint corresponding to due variable, primal variable corresponding to the due constraint. In this primal formulation, we can see that the current basis is -1 and -1 on the diagonal, and off diagonal 0. So actually the B matrix currently is a negative identity matrix of dimensional 2. And this is also equals to its own inverse. B inverse is exactly equals to that. And CB equals to all 0 because x4 and x5 are currently the optimal, the basic solution. Look at the Y column. Y columns actually equals to what? B inverse times AI equals to negative AI inverse. So I basically have to flip the entire multiply these two equations by -1, okay, on both sides, and make it all of them are negative. Let's look at, and Zj minus Cj's, okay, Zj minus Cj are actually negative Cj right now, initially, because Z initially equal to 0. They're all less than or equal to 0. That's finally my basic variable equals to B inverse times B. We know that B inverse equals the negative identity matrix equals the negative identity matrix times B equals to negative B. So basically we multiply these two constraints both sides by -1. Look at the tableau we put it in, okay? On the top, Zj minus Cj, all negative, okay? Objective function value is 0 for now, and each one of the constraint I multiply negative and put it in. The right hand side are -3 and -4. So we notice this particular simplex tableau, all the column row 0 right here, the Zj minus Cj are negative, so actually we are at the optimal tableau, and actually in this case we call it super optimal tableau. But you have a primal infeasibility because your basic variable right now equals to the negative. So what do? We choose, based on the algorithm, choose the most negative one, which is a -4 right now, as the leaving variable, which is x5 is leaving. Then we look at only the negative entry right here, -2, -3 is right here. Using the row 0, Zj minus Cj, divided by these elements. So it's -2 divided by -2, -4 divided by -3. So choosing the minimum one, because negative divided by negative will be positive. So we're still choosing the smallest one. So that means x1 is entering in this case, and x5 is leaving the base. So what we do is we basically want to have this pivot column. The pivot column looks exactly like the column x5, okay? So the last element equals to 1, and rest of the rows equals to 0. So that's after one pivot. This is what we get. But we still have all the row 0 right here are negative. Okay, we know we are still in the optimal tableau. But right hand side, we have a -1, which is x4 equals to -1. So we're going to choose that as my, okay, we're going to choose that as my leaving variable. x4 is leaving. And then we look at the negative elements right here, -2, 5/2, and -1/2. And also using -4 divided by -2, 5/2, and -1 divided by 1/2. Okay, and my minima will be x2. So therefore, x2 is entering the basis, x4 is leaving the basis. So we're going to do another minima ratio test, like we said it before, and then do a pivot. Okay. Make x2 column looks like x4 column originally, and that's my after pivot. We can figure it out. We want you to pay attention. This is a maximization problem. X4 and x5 are surplus variable, and you can see that this is my negative, actually is my negative omega, which is the two due solutions right on the surplus column and the row 0, and then we can check that all the right hand side are positive right now. All the right hand side. All the row 0 are less than or equals to 0. So I know we have a primal feasibility and the due feasibility, okay, due feasibility, and then we add the optimal solution. And this is how due simplex method is doing. So I want you to kind of pay attention. So due solution is just the opposite. You maintain the row 0 are all negative to, or 0 to begin with, and your right hand side you have some negative to begin with. You choose the leaving variable first, then based on the minimum ratio test, then you choose the entering variable in that regard. Okay?
You're at 22 minutes.
We're going to stop till this slide. We're going to